Hey guys, today I'll be explaining or trying to recap what I learned in Physics 256. I'm just trying to make sure you guys, like I can see. Yeah, I think this is just in frame. Okay, Physics 256, Quantum Mechanics. So this was another course I took this semester at UofT in my second year. It was very fun, super interesting. I am doing a physics specialist, so genuinely I'm interested in this stuff. And we actually got a lot done. Like, this was probably the most challenging course in the sense that it was the course in which I learned the most new material. It was completely counterintuitive, like not even counterintuitive. It was very hard to grasp the language that people use to describe quantum mechanical phenomena. But okay, first things first. I'll just go like a brief overview of how we went about the course and explain stuff or try and explain things like very simplistically as we go. We first talked about complex numbers. Complex numbers play a huge role in quantum mechanics. It can be argued that in some parts of physics, complex numbers are just a mathematical tool, but some other people argue that in quantum mechanics especially, complex numbers are a necessity somehow. I don't really quite get how it works, but quantum mechanics wouldn't work if we don't use complex numbers. There's something intrinsic about it, and that has led people to argue that complex numbers are really an element of reality, which is obviously fair. I can see that. Like, there's a whole philosophical debate about it, and I am for complex numbers. So we talk about complex numbers, and basically the main formulas where you can describe it as you can describe a complex number as a plus ib, where a and b are real numbers, which is equivalent to some r e to the I theta, which is Euler's form, which is also equivalent to what was it, r cos theta plus I sine theta. So all of these are equivalent forms to write complex numbers. That's one thing we did. The second important thing we kind of had to get out of the way was matrices and eigenvectors and eigenvalues. A quick overview is that an eigenvector is basically a vector which remains unchanged if you act on it by another matrix, such that the eigenvector is just multiplied by some constant. So if you have some matrix or some linear operator m, and you multiply it with an eigenvector v, or you multiply with any vector v, and if this equals to some constant a times the same vector v, then we call these v's eigenvectors, and this a an eigenvalue. That's basically what an eigenvector and eigenvalue is. But there are obviously ways to figure out how something is an eigenvector or how something is an eigenvalue. To find if something is an eigenvalue, you have to solve something called a characteristic polynomial. So you basically have to solve this equation of determinant of m minus this is equal to 0. So what this is this matrix over here. I is the identity matrix and lambda is just any constant. And when you solve for lambda, whatever values you get for lambda are your eigenvalues. So I guess a more appropriate name, like lambda is just a convention, but because I used a over here, I should have used a over here, or maybe I can change this to a lambda. So yeah, so this is how you find the eigenvalues by solving this equation. Obviously you can see this makes sense because the determinant of m minus it's an equation that you can solve. The eigenvectors you solve by plugging whatever eigenvalue you get into this equation over here. And so you'll probably have something like, if you have a 2 by 2 matrix, assume this is a 2 by 2 matrix, you'll have a b equals to your lambda times a b. You just solve for a and b over here and you get your eigenvectors. Right. So those are the I guess key starting points we had. We will talk about Pauli matrices, I guess, a bit as well. So Pauli matrices are special matrices in complex, not complex, but in quantum mechanics. So you have I think it's negative I, yeah. So you might be wondering what the use of these matrices are. There's an imaginary number there. All these have some uses. I guess it makes more sense to motivate it using the Stern-Gerlach experiment. This was an experiment done by these two scientists. I don't know when, but what they did was they shown, let's say you have like, so like you have like a magnetic field over here, and then you have a beam of silver atoms, I believe it was, and they like, they had like a source which emitted it, and they basically charge the silver atoms towards this magnetic field, and what they found out was they only saw the atoms get deflected in two directions, either up by a factor of h bar over 2 or down by a factor of negative h bar over 2. And classically they expected there to be a uniform distribution, because they believe that, so firstly they hypothesized that any deflection would be because of spin angular momentum, or like an intrinsic property of an electron, which I don't really know why. It could have been argued that the deflection could have been caused by orbital momentum, or like the very fact that there are electrons in this which are moving, that itself generates its own magnetic field. So I don't really know how they concluded that any deflection over here was due to the spin. But so what they did is, but like many scientists believe them, I guess, so there must be something I'm missing. Nonetheless, they shown the atom, they expected a continuous spectrum, but they only got h bar over 2 plus, h bar over 2 minus, and hence they concluded that the electron spin has only two distinct values. It's intrinsic to the electron, and that's where the spin comes from. That's why they call it a spin 1/2 system for electron, because the electrons only have two spins, up or down. These are just conventions, I guess. So this is in the Z, and also in quantum mechanics, there's a whole thing about like bases. So you can choose the Z, X, or Y basis. Z is the convention. Normally we always work with the Z basis. X and Y is basically you flip the Stern-Gerlach experiment 90 degrees to get where the electron would move in the X and Y direction. So what these people found out was, if you shine this beam of silver particles through this thing, through this Stern-Gerlach analyzer, and if you measure them to be in the plus h bar over 2, right? And then let's say you shine the silver atoms that were detected at the plus h bar over 2 through an X analyzer, which is basically this thing inverted 90 degrees, you will find out that there's an equal probability of them going in the plus X or minus X. I don't know how to draw that, but so like how you have h bar over 2 here, now so they have an equal probability of going plus h bar over 2 or minus h bar over 2 once you like tilt the, or like flip the Stern-Gerlach analyzer. And then what they noticed is, if you again, let's say now you take this negative h, like the silver atoms that were detected in the negative X place, and then you shine it through another Z analyzer, you again get equal probability of going plus h bar over 2 minus h bar over 2. That is kind of shocking to at first, because remember the chain of events that led to this. We first shown the electrons through a Z analyzer. We found out that they're all in the plus Z. They all have spin plus up, or like up. And then we put the electrons through a X analyzer, and then we took the negative h bar over 2 electrons, and this could be replicated with either one. So for either one of these two places, you put the electrons back into a Z analyzer, you'll get an equal chance of it being in the plus h bar 2 and in the negative h bar over 2. That's surprising. But let's say instead of just choosing one, you merge these electrons again somehow, and then you shine it through another Z analyzer. Now you'll only get plus h bar over 2 electron. Like electrons only will be deflected up, they won't be deflected down, which is kind of crazy. Like that's one of the stuff that they found out, which like kind of kick-started quantum mechanics. Other stuff we can talk about is, we talked a lot about polarization and how quantum mechanics, I guess it's my Professor Steinberg, he does a lot of stuff with light, and so that's why he basically organized this course a lot around light and polarization of light, and how those two are very similar, like how all quantum mechanical concepts apply to polarization of light. But nonetheless, I wouldn't go that deep into polarization for now, because I'm just doing the basics. Okay, so in quantum mechanics, we also have these things called kets. I'm sure you guys must have seen some notation like this, where like you have some stuff within these, like a straight thing and like a crocodile bracket, and these are called kets and bras. These are like basically the language of quantum mechanics. So how we have normal vectors that we denote it like this. In quantum mechanics, we denote the vectors like this. And these vectors are not ordinary three-dimensional vectors. They live in a much more complex and rich space called the Hilbert space. I have no idea what that means, but it's math basically. I don't really know if I should trust it or not, but that's what we have been told, that it lives in the Hilbert space, which again doesn't make any sense. There's no point personifying these vectors to have human-like capabilities of living somewhere. Nonetheless, okay, we do a lot of our math using these cats and bras. So some other rules that you should probably be aware of, like I'll again go in terms of electrons. So plus, so this is a cat, I believe. I always get confused between bras and cat. I don't know which one is which. I'll get flamed if this is not a cat, and I'm gonna say this is a bra. So why we have these two different things? This is just the complex conjugate of each other. So this can easily be written as, I should not put that there, as a complex conjugate. And from complex numbers, we know what complex conjugates are, but how do you take the complex conjugate of a bra? You just invert the bracket. It's literally like that. Normally the case is that you have some coefficient in front of the vector, like you know how we have, so if we have this coefficient in front of this vector, and when we take the complex conjugate of the entire thing, this coefficient can in general be complex. It can be, I don't know how that symbol is for complex, but yeah, it can in general be complex. So when you take the bra of this, you get the coefficient complex conjugated. So let's say you have I this, the bra would be negative I this. But if you just have 1 or like 2 this, the complex conjugate would just be 2 like this, right? So it really depends on the coefficient. Now these cats need to have special properties. They must be orthogonal, they must be normalizable, and they must be complete. What that means is how in ordinary geometry we have these unit vectors I, j, k. These things can describe the complete three-dimensional plane anywhere you are. If you have these 3 vectors, you can get to any point. Similarly, in quantum mechanics, if you have a basis that can completely take you to any place, what is it called? If you have a basis, so if you have a complete basis, then you can probably get anywhere, right? That doesn't make any sense, but let me tell you. So for example, in a spin 1/2 system, there are only 2 possible options, either up or down. So that's your basis. You're either up or you're down. And what that means is your cats would be plus or minus. And this is all it's saying, that this forms a complete basis in the sense that, you know, I can get any superposition of plus up or plus, I can get any superposition of plus or minus, or any state in general. Or any electron can be described by just these 2 things. So like, let's say I have an unknown state of electron. I don't know what it is. And you know, in quantum mechanics, it's all random. It's like, oh, what probabilities? My electron can be up, down, anything unless I measure it. But sometimes they might have a higher probability of being up or a lower probability of being up. And that all information is like, you know, conveyed by a general ket. And this will basically be some coefficient of the plus of like the positive basis plus some coefficient of the negative basis. And this basically tells you the probability of what state the electron is actually in. And what this is actually, how this links back to this is that because these 2 are basis vectors in the Hilbert space, these 2 must be orthogonal. Like, you know how these 3 vectors are orthogonal in the sense that if you dot I with j or I with k or j with k, you always get 0. Similarly, if you dot the positive ket, the plus basis, I think I'm misusing the terminology a lot here. If you dot these 2 cats, which are in opposite, which form the complete basis, you basically get 0. But if you dot the same cats, you get 1. It's similar over here with the stuff over here, with the normal 3-dimensional place, right? So this is what the properties. These are the properties the cats hold. The next thing about these cats is that, you know, remember the coefficients I was telling you guys about? So if you have A plus B, if this is the state of a general electron and you want to find the probability of, let's say you want to find the probability of the electron being deflected up. So you want to find, like, if you pass it through a Stern Gerlach analyzer, you want to find the probability of it going up. You basically take the, what you do is, the probability of finding it up, the way to calculate it is you take the bra of the probability of this vector's probability that you want, and you dot it with the general ket probability. So what this will looks like is you have this, and then you have a, so I'm just expanding what the general ket is, so I should have put that there, plus b minus. And because in all this is linear, and in quantum mechanics I've asked this quite a lot of times, but we haven't really come across any non-linear examples. There could be, but in quantum mechanics this year whatever I've learned is all linear. So this can just like, this just distributes, I guess, in some sense. So you'll have plus a, so some coefficient, and because these are coefficients, they don't really interact with the vector, so they can just be moved out. And you know what you get is, you get these things. And from our rules before, we know this is 1 if you dot these two things, and this is 0. And hence the probability to find the probability amplitude of the ket of the electron going in the plus h bar over 2 direction is given by A. It is important to know that this is the probability amplitude, and in general it can be complex. To find the probability, you take the complex square, or the mod square, or something. It's the square. So you basically multiply A with its complex conjugate. This is the same as A multiplied with its complex conjugate, and that gives you the probability of finding the electron. So this is simple, obviously. Well, it's not very simple. I'm sure you guys are like very confused, because there's a lot of questions I had asked, and I don't want to get into all of them right now because of time limits. But and I want to like really get this done, because I want to move on to like other subjects as well. But if you want more information, just let me know. The convention we normally use when talking about probabilities is whatever probability we want to measure, we put it in the beginning, and the input. So let's say I'm inputting a particle which can be described by a general ket. The entire information about a particle can be encapsulated in this one general ket, which can be given by some bases, which just has like it basic, and these are just two bases. And this is because it's only in the spin electron 1/2 system. There could be other systems which might have an infinite basis, or many more, right? And the general information about that entire particle will be given by this general ket. And let's say I have a ket like that, and I want to measure the probability of getting one of the bases out. So my input would be this ket, and my output would be the measurement I'm trying to measure. And by doing so, I'll get the probability of what I really want to measure out. Okay, there's a lot about polarization in my notes, which I don't want to get to. We learned about the projection postulate and operators. Okay, oh my god, this will be so hard to, anyway, that's for me only. So we learned about operators. An operator is just a matrix which acts on a ket. So remember these Pauli matrices I was telling you about? Like all these things here, these are all operators, and they act on certain systems to give out specific values. So let's say I take the Z Pauli matrix, and so that was I think 0, 1, 1, 0, 0, -1, I believe. Yeah, so this is the Z Pauli matrix, and if I multiply this with A, B, this if you carry the multiplication, you'll probably see I get A0. Wait, no, I don't. 1 times, oh no, I get A -B. Right, now that makes sense. Why does it make sense? Fuck, I have so less sleep. What is the Pauli? So okay, what these matrices basically do is, let me just go a step back and try to understand why this makes sense. I thought that they used to just give me back the, oh no, okay, no, I'm messing it up a bit. Yeah, no, forget about this. I don't think I understood this properly then. Ooh, that's interesting. Okay. we have something called an expectation value. Let's move on. It's almost 20 minutes. I want to get this done under 30. We have something called expectation values we learned about, and expectation values are normally of operators. So this is this operator here, the Z operator, and the way you calculate expectation values is you calculate expectation values of this matrix. First things first, the expectation value is not the most expected value. It's a very tricky system these guys use. The expectation value is just the average value that you expect to get from a system from a whole bunch of measurements. So let's say in the electron case, you have plus h bar over 2 or minus h bar over 2. These are the two possible situations. The average of this is 0, and so that's the expectation value. It's not like which one is most likely to occur. It's the average. It's literally the average. And the way you calculate this is you take the bra of the general state vector, you put in this operator over here, and you act the operator on the ket of that vector. So this will act on this vector, and then you just take the dot product of these two, and whatever value you get, that's the expectation value of the operator you have. Okay, what else do we have? Oh, we have the uncertainty stuff. So this is not like the uncertainty principle, but the way you calculate the uncertainty in an operator. So let's say you have an operator A, and you want to calculate its uncertainty. This is given to us by the expectation value of that operator square minus the square of the expectation value of the operator. That will give me the uncertainty of that operator, whatever that means. What does it mean for an operator to be uncertain? I don't really know. I see. There is this other talk about a Hermitian matrix. And a Hermitian matrix is any matrix which obeys the rule that the complex conjugate of the Hermitian matrix is equal to the Hermitian matrix itself. So when you transpose it and when you complex conjugate it, the rows and columns always remain the same. Let's see, what else do I want to talk about? We have the projection postulate. The projection postulate basically tells you that once you take a measurement of a system, that let's say I have this general state of electron. Once I measure it to be in the plus, once I measure it that it goes up, it collapses the entire system, and now the new state of the electron is actually just this. That's the new state, because I know it's gone up. So that is the new state of the electron. And that's what the projection postulate basically tells us. It is given to us by, so if you want to find the new general state vector of a particle, let's say you make a measurement of the plus basis, and you find the probability of it happening in the plus basis, and you do that by you get the probability amplitude, and then you have to normalize it. It's something along those lines. That's how you use the projection postulate. We've talked about the commutators. Commutators are quite important in the sense that they tell you, you learn about, I'll talk about this later as well, but if something commutes, it basically tells you whether you can know two things simultaneously. So for example, an operator, okay, I should also mention these matrices that I keep calling operators, these always correspond to observables. And an observable is anything that you can measure. Anything that you can measure is an observable. Let it be position, momentum, energy. Yeah, all these things that you can measure, these are, I don't know what else, angular momentum, for example, as well. These are all observables, and hence operators. And hence, like, operators describe what these observables are. So when we do commutators, we talk about commuting observables. So let's say we have two observables A, B. This is how we define the commutator as. So in our case, we can take the Pauli matrix, for example. This can be sigma z, and this can be sigma y, and whatever result we get over here is called the commutator of these two matrices. And I think for these specific matrices is some IH bar, one of the other Pauli matrices times one of the other Pauli matrices, right? But let's say this is 0 in any situation. Then it means that we can know the two things absolutely simultaneously. We can know, for example, if you take position and momentum. Now the reason the position and momentum you must have all heard about is that you can never know them two simultaneously. One of the places where that comes from is that the commutator of the position and momentum does not equal to 0. It equals to, I believe, I something. I'm not quite sure. Probably I'll get to it. I think it might be IH bar as well. But yeah, and the uncertainty principle comes from the fact that delta A, delta B, these are two observables like I've mentioned, is equal to 1/2 the absolute value of the expectation value of this commutator. So these this commutator will give you back a matrix because this operation gives you a matrix, and then you take the expectation value of that matrix and then you mod it, like you take the absolute value without the complex stuff, and that's the uncertainty principle. And this is where you get the 1/2 h over 2 pi, was it? Yeah. So that's where the uncertainty principle originates from. Okay, a lot of good stuff. We talked about multi-particle systems as well, and the thing with multi-particle systems is if you have two particles on which you're doing experiments on, we normally write them as so on until d. Yeah, I'll probably just add in the C over here as well. So this is like a multi-particle system state. Before we only had like one, but now we have like several particles. And the more formal way to expand this is, it's the first particle tensor product with the second particle. And any operation we do on these systems, let's say we're dotting this entire ket with an observable that only affects particle 1, then we will only act on particle 1 with that observable. For example, if I have some operator S1, right, and I have some particle 1 tensor product with particle 2, this is just gonna be S1. Sorry, let me write it down here. S1 tensor product with particle 2. It will only act on its own system of particles. So that is, I guess, multi-particle systems is quite easy actually. Multi-particle stuff. One more other thing I should mention is, again, just going back, this is like all stuff I learned before term test 1, and the probability of interference is very interesting as well. I don't agree with it at all. I don't even understand how it was derived. But what these people found out while doing experiments is, if you notice that a particle is taking a certain path, there can be no interference at all. But if you don't know if there's no way you can find out which path a particle is taking, then interference will occur. And for example, if you have the double slit experiment, if you don't know which path the slit takes, the probability of the diffraction pattern of where the maximas and minimas will be is given by A1 plus A2 square. So you sum the two amplitudes, where A1 is the probability amplitude of the first particle, A2 is the probability amplitude of the second particle, and you add them and you square it. This gives you the probability of okay, so this is interesting. I don't know if this is the probability of the interference occurring. Like, I know interference will occur, but is this the probability of where the max and min might happen? Probably. Don't know about that, but yeah. But let's say you notice where the particle is going through, right? Then the probability becomes A1 square plus A2 square. Now, I'm just as confused as you guys. Like, where did they even come up with this? How did they come up with this? What's the derivation? I have no idea. Like I would like to know, and I've asked my prof as well, and he normally just references a bomb experiment, and yeah, you could never quite understand it. Nonetheless, getting off topic here, I'm just looking through what other stuff I learned this semester from pre-term 1. Yeah, no, I think, okay, so this is all the, not obviously all this, so much more. But now that we have the basics, we come to Schrodinger's equation and time evolution and all that stuff. So Schrodinger's equation deals with waves of, it's basically particle wave. It's a theory about, it's a wave theory basically. And how we were all dealing with like cats, which were discrete. You could only have up, down. A base electron could only be up or down. Now we have like, the probability is more continuous in a sense. And this is especially useful if you have something like position as an expectation value, position as an operator, right? Like you can have an infinite number of eigenvalues for position. Oh, one important thing I forgot to mention is in these operators that we have, 0, 1, 1, 0, the eigenvalues represent an observable. So let's say you make a measurement. The only possible values you can get are the eigenvalues of the observable. Let's say you're measuring spin. The only possible values you can get is up or down, and those correspond to the eigenvalues because the Pauli matrices have eigenvalues of plus or minus h bar over 2, which you can like try it out and find out. But yeah, so instead of using a general vector like that, we switch to psi of x, which tells us the complete state of the electron. It gives us information of not only position but also momentum, and that's what we'll be talking about. The momentum eigenstate. Ooh, okay. Wow, now this is getting interesting. I should have probably talked about the position eigenstate first. I'm still trying to figure out where all my proper notes are. Just give me one sec while I... Okay. You know what? Let me actually talk about the Hamiltonian first before I dive into Schrodinger's equation, because I think that makes more sense to me. Right, okay. So the Hamiltonian determines the energy states through the energy eigenvalue equation. So the basic equation of an Hamiltonian is another operator, and it just tells you all the possible, well, it deals with energy of the system. So if you have an Hamiltonian with an eigenvector, with this eigenvector, you basically get the eigenvalue back as you would expect, and this eigenvalue will basically tell you the energy states that the particle can be in. And since we know that the total energy of a particle, or the total energy of anything, is given by the kinetic energy plus the potential energy, right? Kinetic energy can be written as p square over 2m, and potential energy, we'll just leave it in terms of v of x. Remember, p square is an operator because it's momentum. It's just something to remember. And let me just put an x over there because we are only dealing in one dimension right now. And since this is the total energy of any system, we describe the Hamiltonian operator to be the kinetic energy plus the potential energy. That is and over here, x is also an operator because potential is dependent on where you are on your x-axis. But yeah, so this is what the Hamiltonian operator looks like. And how we use this is basically, for the general state, instead of using psi of x, we normally use this to only talk about positions. We use something like this to talk about energies. And this is like the eigenvector of an energy if you're measuring energies. So you get something like, bam, that's the equation of that's the energy eigenvalue equation is what we call it. And the way we convert between operators and actual values is, the operator of x is just equal to x, but the operator p is equal to negative I h bar d by dx. This is so interesting how we came to this, but I unfortunately won't be able to talk about it because it's a lot. If you want me to talk about it more, I will. But yeah, probably no one wants me to hear that right now. So if we just plug all of this back into this equation, what we get is p squared, so that'll be negative h squared over 2m d squared over dx squared plus v of x. This entire thing gets dotted with or multiplied with the eigenvector, and this will give you some energy. I should not, this is like a general equation, so I'm dropping the index I. Right, I think this is pretty much the main energy equation we will use. What was, yeah, this is the main equation we will use. Let's see where, I think I should probably just introduce Schrodinger's equation here as well while we're at it. Schrodinger's equation is literally the same thing, but we have the Hamiltonian, which we multiply by a general state vector. Oh, this is like a wave function, not a vector anymore. And we get this stuff back. Now, I'm sure most of you have not realized this. I wouldn't have. But these two equations are exactly the same, because think about it. You have the Hamiltonian, which I have said describes the energy. Bam, that's where your Hamiltonian. Oh wait, no, my bad. This Hamiltonian is like over here, I guess. So the Hamiltonian, like I said, is this stuff over here, right? Now if you multiply this with a state vector, you basically distribute it. So now I have my kinetic energy that goes here, and I multiply it with this. I have my potential energy that goes again, gets multiplied with the state vector, and that is Schrodinger's wave equation. This is the energy equation. Sorry, these are not equivalent. This is how we solve for energy eigenstates. Okay. Yeah, I was right. The commutator of x and momentum is IH bar. Right. What other stuff that I should be talking about? Okay, so now that we're in waveform, we have like special normalization conditions. We take an integral instead of summing them. So the probability from negative infinity to infinity dx would be, the probability from negative infinity to infinity of the wave function spread across all of space is what this basically means. And this must equal to 1. Then we say it's normalized. And in quantum mechanics, we always want our probabilities to be normalized because we want it to add up to 1. We talked similarly about expectation values and how to find overlaps between waves to find the probability of a wave being in a certain state. But I'm kind of like tired and wouldn't want to go into that right now. Or I should, but it's fine. Okay, let's talk about an infinite square well. This is the next thing we did in quantum mechanics. So basically in an infinite square well, you have a particle that's confined within this well, and the potential here is infinity, the potential here is infinity. Over here it's zero, it's infinity all over this place, and it's 0 inside the potential. And we're going to use the Schrodinger's, or we're going to use the energy eigenvalue equation to solve this. Because the potential is infinity everywhere outside, we can break the energy eigenvalue equation into 2 steps. We can talk about what happens outside the box. So remember, the equation is p squared plus, it's ke plus the potential is equal to the energy, this entire thing is multiplied by that vector, right? This is what it means. But now if we're talking about outside box, this thing is infinity, and the only way for this equation to make any sense is if this stuff is 0, this vector over here is 0, which everywhere outside the box the wave function for the energy is 0, which just basically tells us that there is no There's no way we're finding a particle outside the box over here if it's infinity, if the potential is infinite outside. Now the next thing you can do is consider the inside box situation where the potential is 0. So now you just have Ke plus 0 times this. What is this? Is this a... As far as I know, that's the energy wave equation. Okay, equals to E, right? And what we immediately notice is we can decompose this, and what we get, if I actually expand the Ke term, what I get is the second derivative of my energy wave equation must equal to negative 2m E over h bar square times the wave equation. Now this is super similar. I'm sure everyone in classical mechanics knows this equation. This motion is very analogous to simple harmonic motion, where you have the second differential of a function being some constant times that same function, and that thing will oscillate with this frequency. No, I almost made a great mistake. That is not correct. It might be oscillating in space, but the thing with simple harmonic motion is this is a time derivative, a second time derivative, not a space derivative. So no, this is not simple harmonic motion. Looks very similar to it though, which is why we can come to a conclusion that because it was similar, we decided that maybe this might have some value, this constant over here. Let's give us a new name, K. And we call, sorry, this is K square. Yeah, so this is basically negative K square E of X, right? And from, again, classical mechanics, we know that an equation of such form, a second order linear differential equation, a solution to that is a sine x plus b cos x. And we talk about boundary conditions a lot. Depending on what the boundary conditions are, we get values for a, b, and there should be the frequency here as well, right? It's a sine kx, b cos kx, and k. So we get values for a, b, and k. And if we get that, then, well, we basically got the wave equation of the energy. And if we get k, we basically got the total energy that is in the system, right? And that's all we want. We just want the energy and the wave equation. That is what it means to solve a wave equation in the first place. That and all is fine. We can do it. And this is how we basically work with infinite wells. With finite square wells, the inside box situation is very similar. But now, outside the box, we don't have infinity, but we have V naught as the potential. And so the outside box situation becomes Ke plus V naught of x times the wave equation equals to this stuff, right? And we define this new stuff. So like if we expand all of this again, and we only keep the second derivative, because Ke has the second derivative term, we can move this V naught x to the other side and do like algebraic manipulations. And what we get is, we get the second derivative with respect to space as 2m V naught minus E divided by h bar square. This is what we get, and we call this Q square. And we again similarly solve these equations and find values for a sine x plus b sine kx, a sine kx plus b cos kx. We actually get several possibilities, because waves can exist outside the box, inside the box, and again outside the box. So we have three different wave equations, one that corresponds to this, one that corresponds to this, one that corresponds to this, and they're all interconnected by their boundary condition. It should all be because in reality we don't really like discontinuities. It should be a smooth transition from outside the box to inside the box. With all this, we kind of work and figure out what the coefficient of the wave function should be, and what the energy of the system actually is. Okay, now let's talk about the simple harmonic oscillator. This stuff was a whole nother interesting bunch. A simple harmonic oscillator basically is the same thing as in classical mechanics, how we have a normal oscillator. um how do I even start about this? We define these new up ladder operators, a dagger and a dagger takes you up a level, a takes you down a level. These are not Hermitian because they don't really represent anything observable. And you know, after a lot of math and a lot of stuff, we find out that if we make all the necessary simplification, then we can write the Hamiltonian as h bar omega times a dagger a plus 1/2. This is the Hamiltonian, I guess, for a simple harmonic oscillator. And it's not that difficult to work with simple harmonic oscillators, I would like to think. There's this other stuff that's really interesting, which is time dependence. So far we were doing like time independent stuff, but like let's say you want to predict the future and you know something is changing with respect to time. What you basically do is you take your wave equation, and this is like a set formula, I guess, somehow, which I don't know how they came up with, but they just figured out that if you have a general wave function x of t, the time evolution is just given by whatever the stuff was with respect to x. So like however they represented it in x, you know, that could be some cn, some sum of, you know, cn. And what you do is you just multiply this with this factor of e to the negative I en t over h bar, where this is like the energy corresponding to this wave function, I guess, and the t is the time, and that's h bar down there, and that is the time in the time evolution. What we find out is that the probability is time independent. You only need the initial state, and the probability will always be given by cn square, and the expectation value is also time independent. So I guess let me just say, like, if you have a general, like as an example, x comma 0, this would be 1/2. Let's say we have some particle that's in this state over here. My pen's about to run out of ink, and I think it's just in time. The time evolution will be given by first, okay, this is the first step. The time evolution would just be multiplying each of this particle with their own respective energy. So like let's say that's 1, so 1 t over h bar plus 1 over root 2 e to the I e2 t over h bar. And now if you want to find with respect to x and t, you basically oh, and of course this is like again, so you have to like add those kets in there as well, and then the kets are like wave functions obviously now, and these have their own wave representations, and so this would just become 1 by root 2, where I replace the ket e1 with its corresponding wave function, and then this just comes down similarly over here, e2, and the e factor just comes down, and that's the time evolution. We talked about transmission and reflection probabilities. Okay, and we figured out, with a lot of calculations, what the ground state energy of the simple harmonic oscillator is. It is, I'll just write it down, it's h bar over 2, and with each successive step, like each time you go higher in the oscillator, it just gets added on by a factor of 1. So the first energy level would be 3 by 2 h bar, the second would be 5 by 2 over h bar, and so on. And I think that should probably be all that I would want to talk about. There's oscillations of expectation values that we learned in the simple harmonic oscillator. If you have an oscillator like that, the expectation value can oscillate, and we have to calculate that. That was a question in the exam. And yeah, I think that's pretty much all there's obviously like all the details I never went into, and I did such a poor job of explaining most of these things. But yeah, we learned there was a lot of new stuff. But these were the core topics, I guess. Simple harmonic oscillator, time dependence, infinite square well, finite square well, Schrodinger's equation, the energy eigenvalue equation, multi-particle systems. Oh, we talked about separability as well and entanglement. Never understood that stuff, how that even works. I just thought every particle was entangled, but apparently that's not the case. You can figure out what is entangled and what isn't. Yeah, I think that's pretty much all I wanted to talk about.